Today we're going to start on chapter 18, but before this, I got a notice, and I'm sure you all did, from our CCNY president, Vince Boudreau, on this policy on vaccination. And it's a timely warning that according to CUNY policy, and which is now implemented at CCNY, as of September 27th, you cannot enter the campus unless you have vaccination record or proof of vaccination. And further, if you do not upload the proof of vaccination to CUNY First, you know what CUNY First will do to you? CUNY First will just simply say, deregister. You're not registered at all. Yeah, namely, you disappear. And for those who are with scholarship, with financial aid and so on, it would be a real issue. And this message from Vince Boudreau was that tomorrow is the last day you can register, you can go vaccinate with Pfizer, which is 3 weeks, between the first shot and the second shot, so that by September 27, you will have the full record of vaccination with the 2 shots. And then CUNY First will say, good, you are now still registered. But if not, sorry. But for Moderna, it's too late, because Moderna takes a longer time between each shot. But for Johnson & Johnson, I think it is less time. So after Johnson & Johnson, you need 1 shot Johnson & Johnson, and after that you have vaccination. Okay, I am telling everybody in case. Now, as to how you upload your vaccination card, I don't know. Somewhere in the,
I'm
CCNY.
just doing it, and you just gotta go to CUNY First, and instead of clicking Student Center, you're gonna click vaccine status, something like that, and then it's
Yeah,
gonna
yeah,
take you to the page.
right. I know. It's a lot of things that you have to do. You have to click here, you click there, and then you have to actually upload it. But it's just be aware that in these times, you need to be that much more careful and sophisticated. All right. So I just wanted to announce that and make sure that everybody gets that. Oh, it's pretty easy. Good. All right. The other thing is I have on Wiley Plus put up homework 17, which is basically chapter 17, but it's a very small part of it. There are only 6 questions, and they're all conceptual questions on linear superposition. We already dealt with it in our class, so it's not a big deal, and it's actually like a gift to you, right? And you have it until, I forget now, September something. We won't meet till September 13th, so you have until September 12th to make sure that you do homework 17, all right, for chapter 17. Yeah, I think you have multiple attempts, and I don't know. Wiley Plus has a certain policy. You do 1 attempt, and then if you need a hint, you will then get a little less credit, not the full credit. Instead of 1 point, you may get 0.95 or something like that. Okay. Anyway, you have plenty of time, because next week there will be no classes. Labor Day, and then there's on Wednesday there are holidays. So there will be no classes next week, and we won't meet till September 13th, Monday. Okay? Any questions?
Yes, Professor.
All right.
On Wiley Plus, there are
Yes.
2 chapter 17 assignments.
Oh, really?
There's one that's worth 10 points and one that is worth 6. I mean, obviously, like, I'll do the one that's worth 6. I just wanted to let you know that there are 2 assignments up.
Oh, I see. Well, then that's because you see, I am also struggling with Wiley Plus. They made it into a new platform, and I thought I did it, but then the first time when I did it, I didn't realize that there's a difference between Wiley Plus and LMS, and I got all confused. But anyway, you look for the Wiley Plus assignment, which is 6 points, because that's the one that I, in the end, decided. Okay. And then after the class, I will have to go back to Wiley Plus and somehow delete the other one. So I hope you will know, right? It is the one that is 17 and it is 6 points. Any other? Thanks for letting me know. Yeah, it's the assignment or homework 17 that is worth 6 points. Now that's the one that you are supposed to do, not the 10 points. I forget now what was 10 points all about. Okay. All right. So now let us come to chapter 18 because it's a longer chapter and more stuff in it. So first, I follow the book and they just want to let you know that matter, we are made of atoms and molecules, and each atom actually is the nucleus with electrons circling around it. You don't need to know what is the quantum atomic model, the picture. All you need to know is that we are made of molecules, and molecules are made of atoms that are, like H2O, the oxygen and 2 hydrogen atoms around it. This is a picture of an atom, and the atom is made, the nucleus is made up of what we call protons and neutrons. And protons are positive charge, neutrons are neutral, no charge. And we have electrons circling around it, and the number of electrons circling around a particular nucleus depends on the number of protons there are. If there are 1, 2, 3, 4, 5, if there are, is it 5 here? 1, 2, 3, 4, 5. If there are 5, protons in the nucleus, then the nucleus is 5 charge, 5 positive charge. Then there will be 4 electrons circling around. Yeah, here there are 4 electrons, so I guess the blue guys are the protons and the red guys are the neutrons. So there are 4 positive charge in the nucleus. Therefore, there are 4 electrons circling around it. And the mass of each one of these protons and neutrons, they are very small. 10 to the minus 27 kilograms. But we weigh, I don't know, I weigh what, 70 kilograms? I don't know about other people. Maybe you weigh 80 kilograms, 90 kilograms. You have a lot of protons inside you. You have a lot of atoms inside you. And I have a lot of atoms inside me. And now, this is the mass of the protons, the blue guys, and the red guys are the neutrons. Then you have the electrons. The electrons are even smaller mass than the protons. You see it? It is so much smaller. It's about 1,000 times, more than 1,000 times, 10,000 times smaller. And the electron is much smaller in mass. And the charge of the electron is in units called coulombs. And we will know who is Coulomb later on. And the charge on the electron is 10 to the minus 19. All right, this just to give you a sense of the overall picture of what it is that we are made of And what is this thing that we call electric charge? What is this thing that we call a current? All right. And so now they say, generally, the number of electrons, the charge that we have inside us, is a number of electrons times the per electron is the charge E. This little e now stands for the electric charge, the magnitude of the electric charge. And when we say that I have 1 coulomb charge, or for some of the batteries, I have so many millicoulombs, I have this much charge, that means that I have a lot of electrons inside my battery. All right. And if you now say, how many electrons are there in 1 coulomb of negative charge? Well, you can now say, if this is 1 coulomb, but if each electron is only 10 to the minus 19, that means that the number of electrons there are is of the order of 10 to the 19. That's a lot of electrons. Okay, I mean, just to get an overall scale. But fortunately, that many electrons, they are not running all over my body. I mean, there is a lot of atoms and molecules inside our brain cells. There are many brain cells inside, and there's a lot of electric things going around, but they are not zipping all over like blood. Blood is flowing all over the body. That's okay because blood is neutral. But the neurons here, there's electrons that are zipping back and forth. That's how I'm able to think and recognize that, hey, I am waving over here, I am dancing over there. But it is good that the electrons over this part of the body is not zipping all over. If it was zipping all over, poor me, I would have been, I would not be here. All right. There was just a few days ago, I guess when Henri was around on the beach, there was a lifeguard that actually got zapped by lightning and passed away. That's when all the electrons from the cloud and the ground wanted to meet each other, and because he was wet, because when you're on the beach and there was rain, you are wet, and then water is a conductor. Later on we'll learn that water is a conductor, and when the lightning cloud is thunder cloud is close by above you, the electrons, they like to jump, and they come up the whole body, the surface of the body, and then they jump from this to the top. And that's when you basically have now electrons zapping all over your body from top to bottom, and you're gone. So first thing you learn about electricity is you can actually have static electricity. And we will now say, gee, how do you get static electricity? You rub. If you take an animal fur, anything which is furry, hair, if you rub, it becomes positive. What that means is when you rub, the electrons as part of this atom, those electrons, they are easily removed because you're rubbing. Right? When you're rubbing, you are basically making some of those electrons that are on top of there are some electrons that are close, their orbits are close to the nucleus. There are some electrons that are further away. And when I teach atomic physics, I always like to call those lonesome George. There are some lonesome George which are on bigger orbits, and there are those that are very tightly bound to the nucleus in the center. Those that are tightly bound in the center, they are not taken away because you're rubbing. But the lonesome George, they are easily removed. So that's what happens here. this animal fur or whatever is the furry thing, hairy stuff, or you do this, or they lose their electron, they become positive. But now a plastic, or they call it ebonite rod, a plastic, oh, it does not. It actually, when you're doing this, it acquires, it picks up the electron, it becomes negative. And this thing about when is something positive, when is something negative, well, okay, I take it from my other book, Giancoli. So this is a nice picture. You are trying to charge it, and you can charge it by rubbing, and you then find that it will have a certain, like, it will have certain, it becomes charged. And one thing you discover is that if I have charged it, and I'll take the two of them close to each other, this plastic ruler or whatever strip you have, they like charges repel. Like charges don't like to be, they don't like. If I am somehow positive charge and you are positive charge, I don't like you. You don't like me and I don't like you. All right? Like charges repel, but, and likewise, if this was a positive charge, like what they call a plastic rod, they take two plastic rods together or glass rods together, they also repel. But opposite charges, that's different. If this one is a plastic rod, is positive, and the other one is negative, then they come to each other. They attract each other. So that's one of the basic things about electricity, static electricity, is that like charges repel, opposite charges attract. And now this is an example of a plastic rod that has been rubbed with silk, becomes positively, wait, what happened? A glass rod. A glass rod, what did I say? I forgot myself. A glass rod, when you rub it, becomes negative, right? Didn't I say that? Yeah, a glass rod. Yeah, a glass rod is, when you rub it, it becomes negative, whereas the furry stuff is positive.
Professor, I think you said that the plastic one becomes negative, but you weren't
Yeah.
saying much about glass.
Yeah, right. The plastic rod or ebonite rod, when you rub it, it becomes negative, whereas the furry stuff, they become positive. I will have another slide which makes it easier, but right now, since I haven't yet come to that. All right, so now we already know that like charges repel, and now a plastic rod rubbed with fur becomes negatively charged, and a glass rod rubbed with silk becomes positively charged. Okay, so that's just pictures of it, but that's the thing that we need to know. Opposite charges attract each other. Well, we have already seen it, so maybe this is not so important. It's not so important. Here, this is my favorite slide. It is not from Wiley, it is from somewhere else. Question is, who decided that when you rub the furry stuff, it becomes positive charge? Who decided that when this is positive, and when you take the plastic rod, when you rub it, it becomes negative? You know who decided or who gave that terminology of positive charge, negative charge? You know who? Do you know who is Benjamin Franklin? Have you heard of his name? Yeah. And I even have a picture of him. He is famous not just for giving the sign of the charge. And you notice that this was in 1748. That's way after Monsieur Professor Coulomb. Coulomb spent a long time trying to figure out this. Later we'll learn as Coulomb's law. But Coulomb did not give it a name, saying that when you do this, this is positive. When you do this, this is negative. It was Benjamin Franklin. And Benjamin Franklin is also famous for doing the kite, K-I-T-E. Have you heard of kite? You don't fly a kite? Of course. And now, one thing about flying a kite is that it flies up to the clouds, right? And Franklin was the one trying to study this lightning, L-I-G-H-T-N-I-N-G, right? It is to study lightning, and so he had the kite go up to the clouds, and then, well, fortunately, he knew how to protect himself that he didn't get electrocuted. So he was the one who did a lot on this, but he was also a politician, you know. Anyway, you know the name, Benjamin Franklin. And he sort of decided or listed, and now all the engineers know the list, that asbestos, rabbit fur, I don't know, human hair, that if you rub it, it is positive. But Teflon, plastic, saran wrap, when you rub it, it becomes negative, right? And yeah, Franklin. And when he did this, he was only, 42 years old. Way before he became a big politician. Okay, so now one interesting aspect of this static electricity, and one day you should go to the Science Museum. I think there used to be a science museum in World's Fair somewhere in Flushing. I don't know if it is still open. Or maybe there usually is a science museum. And in a science museum, you will have these things that are called electroscopes. And the interesting thing about electroscope is that you can make these strips, metallic strips, do interesting things depending on what you bring to it. If I take something that is positive and I bring it to an electroscope. Now, originally the electroscope was not electrified. It was just neutral because it's been sitting there and nobody touched it. But now I bring my rod that is positive charge close to it. Then what happens is these are there are electrons and positrons inside here because all these atoms, they are all neutral. But the electrons, when they see, positive charge nearby, they like that. So the electrons, the negative charge, they all rush to this side. So on this side of it is all positive. But on this side of it, I have two strips that are both positive, and the two strips says, I don't like you. Yeah. So the fact that there is a positive rod over here causes my two strips to be repugnant to each other. Okay. And now what happens is, if I now touch it, you see I have this rod, positive charge, and I now touch it. Well, when you touch it, of course, then the negative electrons go over there. But my rod has more than whatever the number of electrons in here, because this is a rod as a whole, a bigger rod. And so the negative ones are eaten up and there are still positive charge on this. Then this whole thing now, I can remove this. I can take this away now. I can take this away, and this now will have the two strips at the bottom now in this sort of like separated. That's how you can charge an electroscope, by induction, by conduction. All right. So this is induction. This is conduction. Because I touch it, it becomes a conductor. And you can now check on the sign of the charge, or by bringing what you know to be the charge. And if you don't know whether this is negative charge, you bring in what you know is a plastic rod, because you have already done it yourself and you have checked with Benjamin Franklin and you know this is negative, and you bring it near. Then what happens is the electrons that are here, they smell, oh, no, I don't, well, maybe you can say, they smell that you are here. Ooh, then they say, I don't like you, I'll run away. And so they then come to the other end of it, and the other end now spreads wider. So you can know that this electroscope is negatively charged by checking on it, by bringing a negative rod, and then when you make it close to this, hey, it spreads wider. Therefore, you say it is negative. Or you can take a positive rod, and then when you bring it near the positive rod, then those electrons that are down here, they say, hey, my friend is up there. So they all run up here. Therefore, there are less number of electrons down here. So there is less of a repulsion, right? So you can actually check on the sign of anything by bringing your own instrument, like this case, a negatively charged rod, in order to see the effect. Do you get the concept? I'm trying to get the concept across. Okay, it's actually fun also. If you ever go to a science museum, you can have fun with it. Okay, now, all right, and in all of these, there is this thing called law of conservation of electric charge. Namely, in any process, the net electric charge is conserved. If originally I have gazillion negative charge and gazillion positive charge, and I touch them, the net result will be whatever is the negative, and then plus the positive, and the net will be, if I have more of this, it will be minus something. But if I have exactly the same, I will have neutral. All right, so that is relatively easy to understand. And we already know, like charges repel. And now this is an application. You know, you can see, like here it says, I see a panel. I am the observer, I'm the user. I see a message here which says SEE, or the message here is I have a certain graph. And what happens is, at the bottom, you have your particular instrumentation, and you have beads, you know, these beads, and the beads are white. If I have now made the part, and this part of my plate at the bottom positive, they will attract the beads because the beads are negative charge. Therefore, above is now blue. So I will see blue here. But if now at this part of the plate, this is now negative, then the beads, which are themselves negative, are repelled by it. So they float to the surface, the top. And therefore, what you see is white. What you see is white. Therefore, you're able to have a visualization of what is the basic circuitry below. And you are trying to give a diagram, you're trying to give a show of a graph of a standing wave, or a graph of an animal, or a graph of, you know, whatever. So this is an application of nothing more than this thing about like charges repel and opposite charges attract. And what you do is you now make these colored beads to be white color so as to give you the white. And if you now have some of them that are blue, I mean a red, you can then have a signal which is red. And now we also come to conductors. In 203, we already learned about heat, that heat flows from hot to cold. Well, in electricity, you also have, if this is mostly negatively charged, net charge is negative, and this is net charge is positive, or what happens is that these negative charges, when they see that there are positive charges over here, they run towards it. And so you will now have a current. Yes, you will now have a current, and it would now be a flow, a current of negative electrons this way. All right, are you with me so far? Yeah. Heat is a conductor. Electricity is also a conductor, right? Assuming that indeed this is a conductor, an insulator is one where it says, no way, I have like a, toll gate, and the toll gate says, I do not allow any electrons to come by. Then that's an insulator. There are many, many materials that are insulators, and it is good that they are insulators, because if my desk is conductor, then anytime there's a little wire that touches this table, I will be zapped, right? So it is good that many materials in our house, like the table, the desk, even your sofa and everything, they are insulators. Only when you deal with inside the computer, inside an oven and so on, or you want to have conductors inside. And then you let the engineers design it so that this microwave oven, that the outer casing of it is an insulator. Otherwise, each time you touch the microwave oven, even while it is going on, you know that it is now doing its job, right? That if the box outside is not insulated, you touch it, you'll be zapped. So just be careful when you have these electrical instruments, electric oven and so on, that indeed that there be safety, how it's been designed. Okay. All right. Now, that's an interesting, I mean, it's good to realize it, but it's interesting nevertheless. You remember Franklin says, this is positive and this is negative. And then you know what Franklin says, if any current flows from positive to negative. Of course, Franklin did not know about electrons. Franklin did not know about electrons. He just says, I already said this is positive. I'm near. I already gave it a name. This side is positive, that side is negative. If you're not connected with the conductor, a current will flow from positive to negative. You follow what I'm saying? In a way, it's not unnatural, right? Is he being unreasonable? He says, current will flow from positive to negative. And even today, when you have a battery, even today, when you have a battery, you have what you call a positive terminal and a negative terminal. Do you have all these remote and you have your TV, you have your whatever monitors, right? You use a remote, and all remotes need batteries, you know, right? AAA, double A, whatever. Yeah, springy side and a flat side. And the springy side is there's a convention. The flat side is the what? Anode, the cathode. Does anybody know? All I know is, yeah, you're right. It's a springy side and a flat side. But actually, if you cathode, no, cathode is negative. Cathode is negative, anode is positive. And that's the technical name. ANODE is positive, and cathode is negative. For a car battery, they just put a plus sign and a minus sign. And when you're jumping, you know, sometimes your battery goes dead and you need somebody to jump. Be careful to connect positive to positive, negative to negative. All right. So now let me come back to this interesting sort of very cute. Ben Franklin says this is positive, this is the anode, cathode is negative. This is anode, this is cathode, and then Ben Franklin says the current will flow from positive to negative. The current will flow. But today we know there are no positive charges flowing. Instead, it is negative. Yeah, right? Ben Franklin thought, well, this is positive, this is negative. Oh, some positive guys got zoom across, so I call it a current. And the current flows, he declares, and all engineers today, electrical engineers, continue with this designation. Current flows from positive to negative. There's a positive current flowing this way. But it turns out it is not positive charges flowing this way, it's negative charges flowing that way. But that's okay, because it's negative charge times the velocity, but the velocity is in the opposite direction. So it is still a positive current. Let me write down this, then you can see it's cute. The current. Yeah, let me write down. The current. Whoops. Somehow, whenever I'm online, I cannot do it. Well, I will. Now I can't even. What happened? Oh, okay. Let me try again. Oh yes. Okay. J is the current. Is the number of electrons moving with velocity v. That's the, even engineers agree, that's the definition of current. Because if I have electrons going this way, if I have electrons going this way, and each electron is carries a negative charge, then the total current is NEV. Oh, then I should put a minus because whoa, oops, there is a minus sign here. Do you see it? Because the electron is negative, right? So the current is the number of electrons. Each one has charge minus E, and they're going with V. But Ben Franklin was thinking of positive charges flowing, and the positive charge, if it were positive charge, would have been flowing this way, from positive to negative. So the fact that Ben Franklin got it all wrong doesn't matter. You're following the cube resolution. V is the velocity of the guy. So in this case, it's actually electrons going. So that's the velocity of the electron. You got it? So even though Ben Franklin did not really know in the end that it is electrons that are running around, his definition of positive current is still correct. It flows, if you want to call it a current, it flows from positive to negative, and it is J, which is the current, is the number of electrons. Each electron is negative E, and V is the velocity of that electron. But in the end, if you think of it as a flow of current, it is still from positive to negative, from anode to cathode. All right, maybe I'm belaboring the point, but it's cube resolution of the. So can we go on now? All right. So now, oh, this is just again the same set of diagrams that you have seen, right? Oh, here is now another issue. I have my originally my metal sphere was positively charged, and I now bring a plastic rod, and I know a plastic rod is negative, and I bring it near, and when I bring it near, all the positive charges come here, the negative charges on this excess negative charges run away, the positive charges come over here. Now, when I don't touch, but I ground this, if I ground this sphere, you know what I mean by ground? You actually connect a wire to this. When you connect a wire to this, then when you bring a glass rod or a plastic rod nearby that has been charged negative, then the negative charges on this sphere, there were some negative charges on the sphere, they all run away. They run to the ground. And it's okay because the ground is very big. So actually there are lots of electrons in the ground. They are running around in the ground, but it's okay because you are insulated from it. You are not, you have your shoes, you have your whatever. So this now shows that I can indeed, if I have a grounding wire, that I can indeed charge this without touching it. This is called charging by induction. So then I bring it away. I know this metal sphere now is charged. It is net charge is positive. Okay. And well, this is just to give you a closer view of. Now we want to come to Monsieur Coulomb. Namely, Coulomb was more interested in what is the nature of the force, because you all know and he has seen that things repel each other. So if you have, for example, this is an example of fiber. So fiber is positive. Fiber is like hair. It is charged positive, and you bring another rod that is fiber. Oh, then this guy runs away. So therefore, there is a force on this guy due to your having brought in a positive rod. And Monsieur Coulomb was interested in, hey, what is the law? Because we all know that there is gravitational law. Gravitational law was in the 17th century, and Coulomb's law is in the 18th century. All right, so he was interested. he was interested in what is the law of force. Well, I download from Giancoli a picture of Charles Auguste de Coulomb. Yeah, it was the 18th century, 1736 to 1806. Well, he actually figured out, and you got to give credit to him, because it was not easy to figure it all out in terms of precise as Newton's law is precise. All right. So what did he find out? By years of measurement, he just took this rod and that rod. And the reason why it was not easy, you see, when you say, oh, I know how much is on this rod, I know how much on that rod, it's not easy to know how much you have charged it, because here I'm doing is I'm just rubbing it. And now it depends on how much I rub it and how hard I rub it, right? So that this rod now may have, 3 coulombs, whereas my friend, he did his and he did, maybe it is only 2.5 coulombs. There is no way in his time to measure how much is the charge you have. It took a long time to figure out exactly how much charge you have. That's because you don't know what this constant is. All you know is it's proportional to Q1, Q2 over R squared. And to know that it's proportional to 1 over R squared also took determination, right? Because you got to now say, I measure, the repulsion between this rod and this rod when it is, let's say 3 centimeters away, and then compare it with 4 centimeters away, and so on. So you have to do a lot of experiments. I don't know how long Monsieur Coulomb did, but must have been years. It's a tribute to Monsieur Coulomb. Newton had an easier life. He had an easier life because he had all the astronomical observations, centuries of it. He had the Kepler's law, he had all these observations of the various motions. So he could then figure out, oh, it is the inverse square law, because only with inverse square law will there be elliptical orbits, right? So Newton, in a way, had an easier time. Monsieur Coulomb did not have years of astronomy, because this has nothing to do with astronomy. It had to be in his lab, and he had to really do experiments to measure what is the force of repulsion at various distances. All right, then we have to give credit to Monsieur Coulomb, and it gives the magnitude, and this constant is in our units. This is the international unit. In MKS units, it's 1 over 4 pi epsilon 0. There's a name for this epsilon 0, but we don't need right now. All we need to know is that it is a number which is in units of Newton, because after all, the force you do measure in units of Newton, and it is meter squared, because this is Newton and this is meter squared over Coulomb squared. And today we know, therefore this epsilon 0 permittivity is such and such, and for both being 1 Coulomb separated by 1 meter, the force of repulsion is 10 to the 9. And here is where you then also say, wow. You know, why do you say wow? Because all you had was a glass rod and another glass rod, And you now say that if the glass rod had actually 1 coulomb, if you somehow were able to rub and somehow really had 1 coulomb in here and another 1 coulomb, and they are separated by 1 meter, the force is 10 to the 9 newtons. Isn't that shocking? Huh? That means that Coulomb force is much stronger than gravitational force. You follow what I'm saying? Newton's law had to do with cosmos, has to do with big scale distances and big masses, the mass of the sun, the mass of the earth. Here you're dealing with these rods, glass rods. And yet, if you were to have fully 1 coulomb on this rod and 1 coulomb on this rod, and they are separated by 1 meter, the force of separation is 10 to the 9. So electric forces are stronger than gravitational force. Gravitational force rule us because the earth is so much bigger. All right? Unit of charge is this. Charge produced are typically a microcoulomb. When you do this kind of thing, it's typically microcoulomb. So anyway, let's now go on. And now this is just to give, to stress or to emphasize this concept that if I have 2 charges, now we begin to say charges, right? If we have 2 charges, this one is plus charge and that one is also plus charge, they each are repelled. And what happens is on this guy, there is a force this way. On the other guy, there's a force this way. And then you remember from 203 that Newton had this law called Newton's third law, that there is action and reaction, that if there is a force on 1 due to 2, there's an equal and opposite force on 2 due to 1, and they don't have to be in touch with each other. You can be separated. In 203, you were talking about, for architects, they usually have a column and then they have a weight on it, and it's usually action reaction. The forces are in touch, in contact with one another. But for Coulomb's force, Coulomb's law, you're not. You could be a mile away and already there's a force on me. But of course, if you're a mile away, the force is weak. I don't feel it. But if you were only, inches away from me, then I would know. And I would have a force on me, which is in this direction, but the force on you would be opposite direction. That's repulsive, and attractive. Okay, so finally, before I give up on this Giancoli, it re-summarizes, and I will call it meet the electron, because the electron is our basic mode of conduction. You meet the electron, you say, oh, the electron has a very small charge, 10 to the minus 19. The electric charge is quantized in units of electron charge. So a proton is positive charge, opposite. And you don't, for the ordinary matter, they are all in units of. Mass of the electron is 10 to the minus 31 kilogram. And today, in fundamental physics, in high energy physics, we actually now know that there are quarks that are 2/3 of the charge. And that will be the up quark, and the down quark is negative 1/3 of an electric charge. But those are not things that you need to worry about because we are made of protons. The quarks are inside the proton, so on. All right, so we come back to this, and now we just want to go over just a little bit of the math aspect of it. They say, well, I'm going over what the book now has. We already have gone through it. It is the magnitude of whatever's the charge, Q1, Q2 over R squared, and the sign, which direction depends on whether it is both positive, then they are repelling. But if one is positive, one is negative, then they are attractive. And therefore, there is a vectorial sign. The force magnitude is this, but there is a vectorial sign, whether it is repulsive or attractive. And this is just as a curiosity. You're not going to be tested on this. The curiosity is, you now say, hey, I have the hydrogen atom, which is the simplest possible atom. Hydrogen atom is one where you have one proton that has positive charge and an electron circling around it. This is what they call the Bohr atom. It's not because it's boring, but it's just Niels Bohr, the model of the atom. And what does the Q stand for? It's the charge. Q stands for charge. Yeah, I should have mentioned that. Emphasize that. From here on in, when we see Q, it means the charge. And if it is positive Q, then it is positive charge. If it's negative, if Q is negative, it's negative charge. And Q would be in units of Coulomb. All right. So just to go over this model of the hydrogen atom, you now say, I have electron in an orbit, and the radius of that orbit is 10 to the minus 11 meters. It's what they call an angstrom. But anyway, you don't have to know that. It is a very small size. The hydrogen atom is very, very small. Each atom is small, but you have a lot of atoms in the water. You have a lot of atoms inside us as a body. And now they say, hey, can you use simple 203 physics to figure out what is the speed of this electron that is circling around this atom, right? You can now say, hey, what is it? Since Monsieur Coulomb has already figured out the magnitude of the force, you know this K, Coulomb's constant, and then you know Q1 and Q2 because you know the electric charge on the electron and you know the sign of the charge of the proton. They are magnitude the same, and you know that the size is 10 to the minus 11. So now what is the actual force? And given the force, what is the speed? Because that's more interesting. Well, you now go through the math. The book has already done it for you. You put in the numbers. K is here. Q is 1.6 times 10 minus 19 squared in these units. And the radius is 10 to minus 11, whole thing squared. So you work it out, and you find that it is 10 to the minus 8 newtons. That's very small, right? You can say, no big deal. If I am subject to that, I would not even notice it because it's 10 to minus 8. But on the other hand, no, don't worry. Don't worry. That's why I'm saying it's this is just for, yeah, it's okay. Haha, you know, don't worry. But it's just cute to say, hey, I can make use of what I learned in 203 to find out certain questions because I'm curious. And the main thing I'm trying to encourage, even for biomedical profession, it's good to be curious. Curiosity doesn't kill the cat. Well, no, sometimes curiosity can kill the cat. But curiosity, when it is based upon some basic concepts, knowledge, does not kill the cat. Curiosity enlarges your horizon. Curiosity enlarges so they're able to think outside the box. All right. So let's come back here. Yeah, the value of K is here. It's a number in these units, 8.99 times 10 to the 9. This is Coulomb having determined it very carefully by his experiments. So this is that constant K. It's a number. Don't worry, you're not to know it by, okay? So now you have figured out, ooh, it is 10 to the minus 8 newtons. But I am more interested in what is the speed with which my poor electron, it is trapped by this hydrogen nucleus, proton nucleus. So what is the speed? Well, 203, I remember. For anything to go in a circle, there must be a centripetal force. And who is supplying the centripetal force? Monsieur Coulomb. Yes, there's a centripetal force. It is this much, 10 to the minus 8. But now, if there's a centripetal force, there is now a centripetal acceleration. But now you remember the formula for a centripetal acceleration. It is v squared over r. Therefore, you can now use the math here, algebra. I can now figure out the v just by taking square root of whatever is the force times r divided by m, because that is the algebra that I need. So now I put in the numbers. I say I know the force, it is 10 to the minus 8. I know the radius, 10 to the minus 11. And I know the mass of the electron, because all these experimentalists have already figured it out through many experiments. And Monsieur, what I find is that the speed of this electron that is trapped in the hydrogen atom is going at 10 to the 6 meters per second. It's quite fast, eh? So do you now have a sense? It is electron inside the hydrogen atom. It is around much faster than any one of us can go. But fortunately, it is not going faster than the speed of light. Speed of light is 10 to the what? Do you remember? What's the speed of light? 10 to the, no, not 137. 10 to the 8. Good. You see, so this is like 100th of that. It is very fast, but it is not the speed of light. And anyway, that's just to get a sense of, boy, we have this hydrogen atom down here, and the poor electron. If I were the guy who is caught in such an orbit, man, I would sort of go a little bit wobbly, yes, because you're going zzz, and you don't stop doing that. Okay, now I have some slides that I say for engineers. It's given in the book. I call it for engineers because then they say, oh, if I have 3 charges here, what's the net force? You know, you can use the Coulomb's law to figure it out. I will say for engineers. From now on, when I want to ignore it, I will give you a signal that says for engineers, okay? And if you ever want to know more, you can go on it, but it's for engineers. Why? For engineers, they have to know now, I have 3 charges down here. What's the net force when I am down, net force on this guy, Q1? The fact that I have 2 guys nearby, now I got to do the vectorial thing and so on. So don't worry, it's for engineers. But now I want to come to a much more important step. Coulomb's law summarized his years of experiment into this beautiful, like Newton's law. It is K, which is the constant, numerical constant, Q1, Q2 over R squared, and it has a sense of direction. But after a while, people begin to take this Coulomb law and separate it. Separate it into two parts. And it is very important. This separation did not happen at the time of Coulomb. It took a little longer because people then begin to have a better sense of how to formulate Coulomb's law in a more modern language. And the modern language is electric field. Okay, the modern language is electric field. And so I now take again from Giancoli, and I now sort of want to summarize this very important fact. And now sort of you need to pay some close attention now, yeah? I have a source charge, namely whatever is the source. And I didn't say what is the magnitude of it, I just say source charge, right? And now I want to know what would be the force on a point charge Q away from the source charge. And you see now, we know Coulomb law says that if you have source and you have your point charge Q, there will be a force on it. But I want to separate it. So first, I want to now know what is the electric field due to the source charge. So here, I will say there's a source charge, and I will now use the language that says a source charge produces an electric field. A source charge produces electric field. You notice I now only have capital Q, and now I have R cubed times R, which means that it's actually still inverse square law if I call this the unit vector. Are you following me on this? I need to get this formulation clear as a concept. I want to now say, if there is a source, capital Q, right? It produces an electric field. Any charge of whatever strength Q, right? Any source charge will always produce electric field. What is the magnitude and direction of this electric field? Well, the magnitude depends on Coulomb's constant, and it is inverse square law, and it is in the direction of the unit vector away from this source. So let's say that I want to know what is the electric field at this point. It is at this distance away. I would like to know what is the electric field here at this point. It is an electric field pointing in this direction, and the magnitude is here. Magnitude and the direction is here. All right. And now, when I have a point charge Q, then there will be a force on this Q, which is due to the fact that it has its own charge Q and it feels the electric field. Are you following my are you following this? Let's say that, yeah, let's say that this is my source charge, right? My handphone, well, fortunately it is not charged, but anyway, this is my source charge. Well, when I have this source, it produces electric field all over. It produces electric field in all directions. It's a field that, you know, you are 10 miles away, you will feel the electric field due to this charge. Of course, when you're 10 miles away, 1 over R squared is very, very small. But nonetheless, the concept is that the source Q produces electric field, F-I-E-L-D, everywhere in space. You are 5 inches away, well, it's 1 over r squared in the direction of, 5 inches away from this. You are 10 miles away, it is 1 over r squared. Doesn't matter how weak it becomes. Nonetheless, there's electric field that comes from this source charge. And now I want to now know what is the force on me. I am that little q. I happen to be sitting here, and because you are nearby, I now feel a force. And it is now the force on you is your charge Q times capital E. And now here there is a very interesting consequence of the separation. Supposing I have no charge, my little q is 0, meaning, hey, I'm overall neutral charge. Fortunately, I am not electrified. I am overall neutral. So you have a electric field due to the high power transmission line, right? There are some people who live under a high power transmission line. I can say, don't worry. There is, of course, a big electric field due to the fact that high power transmission line, they have gazillion electrons zipping by every second. It's gazillion electrons zipping by on the high power transmission line. So there is a big electric field. But I have 0 charge. So don't worry. You see now the advantage of using this language. This language, I take the Coulomb's law and I separate it into you, your little q, because you are the one that feels it. And now I separate it into electric field due to the source. Are you comfortable with this concept? Because this concept is a very key concept. All right? Yeah, I think once you sort of get that picture, it kind of makes sense, right? You kind of like, you then appreciate. Oh, I mean, you want to thank not Herr Professor, but Monsieur Professor, Coulomb, and you say, "Ooh, it's a very good work, to get those precise form of the law, R squared inverse square law with this Coulomb constant here. That is good." But the modern language is to say, I want to now separate it into this field produced by the source and by the force on me because I happen to be here. All right. So the law, therefore, Coulomb's law, now you put it into a very nice form. You just say force is QE. E is due to whatever is present in your space. Then the force on you silly fellow, is because you have a little q. If your little q is, very small, you say no big deal. The force on me I can handle. But if you yourself q has a, appreciable charge, then there is a force on you, and the amount of force on you depends first on your little charge q, what is you charge, and then the actual electric field in the presence of where you are. Okay, so I spent a lot of time on this because this summarizes the new perspective of Coulomb's law. And now we go back to the book, and the book says, okay, the electric field is F over Q0. But I prefer to say that you already have the electric field, and then the force is your charge times electric field. And so now they say, okay, you can now have a situation where you have this rod here, and then you have this metal sphere here, metal sphere there, and then you want to now know what is the force on you. Well, then you will then have to first figure out the electric field due to this, electric field due to this, electric field due to this, and then the net force is here. I should put an engineer for engineers. So this is really for engineers, okay? I was getting sleepy and I forgot to put in. Okay, when I will update it and put back for engineers, okay? And this one is really for engineers. They then say, hey, I have a positive test charge. It has a magnitude of 3 × 10⁻⁸ Coulomb and experiences a certain force. Find the force that the test charge feels and predict the force. Anyway, you know the F, you know the charge, therefore you know what is the electric field. And as I say, this is for engineers, so don't worry. At least I wouldn't worry. And now that you've gotten the concept, these are just applications of that concept. And the fact that these are vectors, so now you say, hey, that's electric field due to A, electric field due to B, therefore the net electric field is to add them. All right, so we will go on because I want to come to a very interesting question. Electric field of a point charge, well, it basically, the electric field is radial. It just radiates from the source. It radiates in all possible directions. All right. If I have a point charge, the electric field from the point charge is in all directions. Okay. And this is just exercises. Yeah, I'm not impressed with this, so let's go on. You want us to go through this? Once you got the concept, this is just working it out. So do you want to work it out or no? Well, you want to work it out? Okay, all right. Okay, you want to work it out. I have a charge Q1, I have a charge Q2. Due to Q1, there is electric field in this direction. Due to Q2, there's electric field in this direction. And I want to know what's the net electric field here. Well, you now just simply say, okay. Oh, and they want to have E1 equal to E2. Namely, they want to know where is the place where there would be net electric field equal to 0. You follow? This is an example where they say, I know this charge Q1, I know the charge Q2, and I want to now know what is the B where E1 equal to E2. Where E1 is equal to E2 means that the place where the net electric field is 0. Okay, well, that's easy because you know the electric field is Q over R squared magnitude K. So you now say the distance from this guy is D, distance from this guy is 3 minus D, because the separation between them is 3. Therefore, it becomes an algebraic equation that says, I want this equal to this, and you can solve it, and it is 2 meters. You see why I call it the engineer application? You basically say, I know Q1 and Q2 both have the same charge, which is 16 × 10⁻⁶ Coulomb. Whatever's the charge they gave us is 16 times, oh no, it's not equal sign. One of them is 4 times the other. So this one is 4 times this charge, right? It is 16 times 10 minus 6. This guy is 4 times 10 minus 6. And now they want to say, where is the point where the net electric field, the net electric field is 0? All right, are you? I am given that this one is 16 times 10 minus 6. This one is 4 times 10 minus 6. And I now know that due to this, there's an electric field in this direction. And due to this guy, there's an electric field in this direction. And they want to now know where between these two guys is the position where there is net electric field is 0, right? Because they want to know where would I be so that I am not pushed by the electric charges. I want to know what point D such that the net electric field is 0. So therefore it then says that the electric field, the force due to this is K due to this 16 times 10 minus 6 over D squared. And then on this side, it is 4 times 10 minus 6 over 3 minus D squared. And once you have decided that you want to look for that place where such that the net electric field is 0, you then find that D is 2. Okay? Can we go on now? Any questions about this? Okay, let's go on. Okay, now conceptual, because I'm more interested always in conceptual, because after all, you are not going to be electrical engineers. You are going to be biomedical professions, and bio profession will not be interested, but you need to know the overall concept and the symmetry because it applies to many situations. So here they say, I have point charges fixed to the corners of a rectangle in 2 different ways. The charges have the same magnitude but different signs. And now they say, okay, supposing this is the thing. What is it now? I cannot read. It's plus, minus, plus, plus. Okay, all right. So I have, I have these 4-point charges, and these are plus, plus, plus in these corners, and this one is minus. And now they say, what is the net electric field? Now, how would you even go about solving it? Let's say to take case A. How would you go about solving it? Well, you can now sort of use symmetry and you say, okay, I'm at the middle, right? I'm in the middle. Now, is there a net electric field due to the presence of plus on this side and plus on this side? Is there an electric field, net electric field due to these two guys when I'm here? No. Yes, yes, no. I mean, I see a yes, I see a no. I don't see no, I don't see yes, yes. I don't see any maybe. I am here. Is there a net electric field due to plus and plus on opposite side of me? No, because both are positive. Therefore, at here, I don't need to worry about these two guys because they cancel each other, right? But now, I'm here. Is there a net electric field due to plus and a minus? Yeah. You see? So therefore, once you get the concept, you can say, very easy. The net electric field is somewhere in this direction. How much? You then have to work out the actual numbers. All right, do you follow what I'm doing? Okay, so that was for part A. That's very easy. Now, what is the arrangement here? You have, you have minus, minus, plus, plus. Your arrangement is you have minus, minus, and plus, plus. So now you're over here in the middle. And then you can say, gee, what is the net due to this minus and a plus? Well, the net due to minus and a plus is here, right? Because from the plus is in this direction, from the negative is in this direction, so therefore it is in this direction, right? And likewise, over here, you have a plus and a minus. Therefore, the net electric field due to this pair is in this direction. And since this is a rectangle, the net magnitude of this pair must be equal to the net magnitude of this pair because their distances are the same. So the net electric field due to this pair is this, the net electric field to this pair is this, and they are equal in magnitude. Therefore, the net result is totally parallel to the side, because this will cancel this. So therefore, you now say the net result of this arrangement is just simply electric field in here, in this direction. So you have already gotten this without doing the math. Okay. And any comments or questions? Oh, yeah, that's a good question. Because remember we said the electric field due to a charge Q. Let me go back to my overall concept. Electric field due to a overall plus charge is away. If Q is positive, it is away. If Q is negative, it is a field coming towards. You see it? If Q is negative, the electric field is towards you. If Q is positive, it's away from you. You got now the sense? So the electric field, right, electric field is away from the positive charge, but the electric field is always coming to the negative charge. Okay? So this slide has everything you need to know conceptually. Numerically, you just have to put in the numbers in the right units, but conceptually, this is the most important slide. And so, for example, when we come back to the question that somebody asked, you see here, this is positive, and the electric field from here is away. This is negative, so the electric field is towards. So there's the net electric field is now towards it. Okay? All right. Now, let's go on. And this now is another example, and it is a common example because we use that a lot. Is a parallel plate, which the engineers call capacitor. And the parallel plate is you have one plate which is fully charged positive and one plate which is fully charged negative. Then the electric field will be from the positive to the negative, and the field strength, you don't have to, I mean, this is what the engineers have figured it out. The field strength is Q, whatever is the charge on this plate, divided by the epsilon 0 times the area. And if I have a positive charge, but it is over a bigger area, then my charge density is smaller. And for there to be a strong electric field, it is really that you have a lot of charge density. Q over A is what you call the charge density. So this is a formula which somewhere later you will find. When we come to electric potential and so on, you will find it. But this is an application of the fact that positive charges are the source of electric field, and these are the field lines. You begin to think of it as field lines, and this then tells you between a parallel plate capacitor, the field lines flow from positive side to the negative side. All right, so now we want to have the full picture of a positive charge. It is radiating electric field lines. The electric field lines all go out because they are dependent, the electric field is dependent on the radius vector. So they are all going out away from a positive charge. But for a negative charge, it is all coming towards. All right. So this then is the language of electric field, that if I have a negative charge, the electric field lines, they all are running towards it. But if I have positive charge, I'm the one that is giving off the electric field lines. So you notice that we begin to have a language that becomes more and more common day language. We first introduced electric field, but now we are talking about electric field lines. You notice? Yeah? Are you comfortable with that? It's just to visualize it. Okay, it's just to visualize it. Okay. All right. Now, in weather maps, you have high pressure and low pressure, and these lines would be the wind, because the wind flows from high pressure to low pressure. So then the weather map, they'll have a lot of lines that show that, whoa, there's this low pressure, and then there are all these wind, and they will tell you the wind is strong and strong. Here, we're not talking about wind, we're just talking about this language that you have the positive charge, they produce electric field, and now you visualize this electric field by drawing electric field lines. Okay, and now we can say, see, when you have a capacitor, well, the electric field lines will go here, but near the edge of the capacitor, the electric field lines will now be sort of like going, bulging out. Why? Because electric field lines from this guy wants to be all over, but it now, because of the negative charge nearby, the negative charge pulling it in, so that's why on the edge you have those that are trying to go away, but they get pulled into the negative. But down here, oh, they are all going this way because there's no other space for it to go, so it only goes straight across. All right, are you following now the field line picture? The electric field line don't stop. They need to end someplace, and they usually end in a minus sign somewhere. If there is no other minus charge, they just go all over into space. Okay? And now I want to come to, well, this is therefore the picture. If I have a positive charge, negative charge, then each one is trying to radiate, and those that are in this direction, they get pulled. Those that are in this direction, they get pulled. Those in this direction, they get pulled. But those that are over here, they basically go very far out before they are pulled over here. They go very, very far out before they are pulled over here. So This then is the map of the electric field line of a system, what we call dipoles. You know, positive pole, negative pole, we call it dipole. And this is a dipole. And this is how the field lines look. Can you kind of like appreciate that concept of field lines, of how the lines end up in a negative charge? All right. Now I want to go on to, and if there are two positive charges, oh, they repel. So these guys, they don't want to end over here. They are repelled. So they all go all the way out. They go all the way out. They go out into space. They don't end. And now that's a very interesting conceptual. You have an arrangement which is minus Q, minus 2Q, and then you have plus 4Q. And now they say, what is the field line? And first question they ask, I discovered that the PowerPoint that Wiley Plus supplied had some funny words in there, but I have changed it to, is there is something wrong with part A. What is it? What is wrong with this picture? Maybe I can, since time is getting short, let me just sort of quickly mention. Yeah, thank you. This one shows the electric field line cross. No, electric field lines don't cross. This is wrong, right? And now you say, is there anything wrong with this? Is there anything wrong with this? It is minus 2, minus Q, and now you have the field lines going over here, and you have field lines going over here, and you have less lines over here. Is that correct? You see, this one is symmetrical with this one. How come there are only two lines going here and there's only one line over here? And this fifth line went over there. Is this right? So this one is also not correct. You got it? You follow what I'm doing? Because they are symmetrical. But now you come over here. This guy looks right. There are lines that go from 4Q to minus 2Q. There is 4Q to minus Q, 4Q to minus Q, and it is symmetrical. See? So the lines are this way. So this is correct. This guy is where the four lines are all squeezed together. That's not right. So out of the A, B, C, D, only this one is correct. Okay, I will end here. I will upload the PowerPoint a little later because I had to correct. What was it now? I needed to correct. I forgot. Oh yeah, that I wanted to put in for engineers so that you know which one is you should know. Any questions before you disappear? No, yeah, I forgot to mention. There is no class next week at all. The next we meet is Monday, September 13th. All right. And for those who are in GH3, you will be meeting at 6:50 with, I forget who it is that is, Anderson. You'll be meeting with Anderson in room Marshak 407 North. Okay. So, all right. Have a good Labor Day weekend and the week off. If you have questions, you can always email me.
Thank you for the class, Professor. Take care. Good night.
Okay, all right, take care. Bye.